All right, so let's now learn about the horizontal scaling of a function. So this is the last, to me, this is the last elementary transformation of a function, okay, or the transformation to the graph of a function. Okay, so let me quickly demonstrate the idea again through the graph for you to clearly understand what it means by horizontal scaling right here. And so, because at some point now we have, in the way how I teach about the transformations, horizontal scaling is usually taught after you have learned about vertical scaling. And so at some times, okay, at some time to some other time, it can be easily confused between horizontal scaling and vertical scaling like that. And so in that way, allow me to do a couple demos like that so that you can clearly see that and be able to distinguish. And then we're going to start diving in formally to understand what causes a horizontal scaling. Okay, so now on my graphing space right here, and with a graph that's currently presented here. Okay, so whatever function that is, whatever function this graph represents, that's not important to know at this point. And then for this function, now I've used the term the guiding points quite a few times already throughout the entire lecture about the learning about the transformations to the graph of a function. And so in that way, this particular graph right here, I use these points right here as guiding points, and I can show the labels here. See, so we have one guiding point right at -2, 0, and then there's one at -1, -1, and so on and so on. So the labels are making it clear about these guiding points. So these guiding points are just simply those points that are useful for defining the shape, okay, defining the shape of our graph. So with this graph right here, and I'm showing this graph in red ink, in the red color right here, meaning I'm going to use this, I'm going to look at this graph as a parent function. Okay, I'm going to look at that graph as a parent function, and this parent function, and again, you don't have to worry, nobody needs to worry about what function gives this graph, okay, what function is represented by this graph, but then in the end, this graph representing a function has a few guiding points that defines a shape. So in the way how I see the shapes goes a straight line, and then zigzag down, zigzag up, okay, wave down, wave up through the x-axis and hit up. So there's a waving section in the middle, and then the two straight lines. So that's the shape for this parent function. So this is what horizontal scaling is all about. So now I'm going to bring the graph back into full screen view right here. All right, so in full screen view, this is what's going to happen. So we will learn what causes this graph to, and now allow me, before I show the demo on the transformation, on the scaling, on the horizontal scaling, now let me bring up a blue version, okay, with the guiding points, with the labels. And so now the blue version right now is the exact same version as the red version. So, and in our study so far about transformations, within my own convention, then blue is a descendant function, for example. Okay, and so the descendant function, let's see what the descendant function still has some characteristic from the parent function, but it's going to be something different. Okay, so let's go ahead and observe the graph now. So with this descendant function right now, currently exactly the same as the parent function, with these guiding points, and everything now just simply turned in blue. Now we're going to study what causes. We're going to study what causes this descendant function to be a sideways compressed, okay, a sideways or a horizontally. See, so I'm using that term sideways compressed. It's being compressed on the side, okay, compared to the original parent function, and the picture is still here, okay. And further, we want to study what causes. We want to study what causes the descendant function to be, okay, stretched, but stretched horizontally or stretched on the side. And so now, what I was saying earlier about, I'm trying to clear up the confusion between, because it's a scale. So stretching or compressing is, to me, it's all about, it's a scaling. We scale horizontally. In this case right here, we're gonna scale horizontally the parent function to create a descendants where it's more widely spread it out or more narrowly compressed in. Okay, and that's the idea. But more widely spread it out, or more narrowly compressed, it's all about a matter of some scaling. Some scaling will cause this horizontal stretch or this horizontal compress like that. Okay, so in that way. But now what I want to clarify, what I want to clear out the confusion is that the kind of confusion that eventually my students will face is that sometimes looking at a scaling right here, you see. So let me put it back in the compressed version. Okay, so for example, with a version like this, due to the fact that, well, and I agree with your observation, due to the fact that at some portion of the graph, it seems like it hits higher. Okay, at some portion of the graph, like say at the straight line portion of the graph right here, it hits higher up, vertically up, and it hits lower vertically down compared to the original parent version. And so in that way, some students, some people at first sight looking at the graph like this, looking at the two versions, the red being the parent and the blue being the descendants, may confuse that what happens here was a vertical scaling. Meaning, so it may be confused as a vertical stretch. Okay, but if we're looking closer, if we're looking a little more closely, okay, and now I can even zoom it in. Now that's why putting in the guiding points are extremely useful, and it makes that clear determination for us, because a lot of times the two scalings right here, vertical scalings and horizontal scalings, can be easily confused together. So let me show you. So if this really is, if this blue version, if this blue graph really was a vertical scale or vertical stretch, because we mistakenly look at this part and it seems like it's getting higher, it's rising higher compared to the red version here. Okay, so we may mistakenly think that it was a vertical stretch. Okay, but then if it was really a vertical stretch, then look at these points here, these guiding points. It happens at the peak. It happens at the peak, so this point should be corresponding to that guiding point. But hey, wait a minute, this point here did not get any higher compared to that point, or in other words, this corresponding point on the descendant function stays exactly at the same height with its parent function. So that tells me right there that it's not a vertical scale, because if it's a vertically stretched version of the graph, if the descendant function in blue here truly was a vertically stretched version from the parent function in red, then every single point will be vertically stretched out. Okay, the y value will get altered for every single guiding point here, and as that's, you have seen that back in the earlier part of the lecture where we were still discussing about the vertical scaling. Okay, but now if we're looking even closer, if we're looking even more closely now, so instead of rising up further out, right, instead of being stretched further out, these points just simply comes closer. Now this point is corresponding to that peak. This point is corresponding to that bottom peak. Okay, they both maintain at the same height. They both remain at the same height, and they come closer in. Okay, same height, but they both coming closer to that the middle, to that center, the y-axis right here. Okay, symmetrically. And then those are not the only 2 points that we noticed that nature, that they maintain the same height, they retain the same height, but they come closer. That's why it shows a compression sideways somehow. Okay, and then this point right here, these two points. Okay, that point is at a peak again. Okay, it has a sharp angle. It's happening at a sharp angle. And then once again, it stays exactly at the same y value, it stays exactly at the same y value to with the corresponding the guiding point on the parent function. But then they seem to stay exactly on the same y value, and they come, but on the other hand, they come closer. These come closer to the y-axis. Okay, so that further confirmed that the scaling we saw here, yes, we saw some stretch, but it looks more like a sideways stretch, a sideways compression. Okay, and then so just like that, we want to study what causes this to, horizontally stretched out. Okay, but see, so I'm using those terms that many other professors use as well, stretching and compressing, but in the end, horizontally stretched, okay, or vertically compressed. horizontally stretched or horizontally compressed. Okay, these are all, to me, all categorized as horizontal scaling. So we learn about the different ways to make a horizontal scaling right there. Okay, and even in the worst case right here, even in the worst case, let me show it right here on the graph. Okay, it's can even have a widely stretched version. Okay, and then flipped. Okay, but this flipped here is more like we flipped sideways. We flipped by treating the y-axis there as the mirror. Okay, so this is called a horizontal flipped. Okay, so back in the earlier part when we were looking at vertical scaling, there were a vertical reflection, or it's a vertically flipped version of the graph. We already learned and studied what caused that. Okay, so here there's also something that causes the horizontal flip, meaning it's gonna flip through the vertical y-axis. Okay, it's gonna have a horizontal reflection. Okay, because it's reflected through the y-axis. All right, so in that way, so a reflection as well. The reflection, a horizontal reflection, is also something that I categorize as a subcategory of all of these horizontal scalings. Okay, so as a matter of fact, when I wrote down this title, it should have been horizontal scalings, because there are many ways we can make a horizontal scaling with that. Okay, all right, and so now let's get to it. So now I'm going to need to erase the title of this transformation right here, the name of this transformation, and then let's get to it. So just like how we learned about the earlier functions, okay, about the earlier transformations, actually, I'm going to introduce a parent function, okay, and then from there we are going to build our understanding. Okay, we're going to build our understanding on a couple of descendants functions like that. Okay, but now when it gets to this far about learning, and for this particular transformation that we're learning, for this particular elementary transformation that we're learning, I highly recommend to learn this. I highly recommend to learn this after you have learned about the composition of a function. Okay, composition of a function. And so at least in my teaching style, I will always teach this after you have learned about composition of a function. But in case this video lesson is learned where you have not had any experience in composing a function with another function, then you can feel free to pause this video and find my other video lesson about the composition of two functions to have that idea at least what it is, and so that we can carry some of that idea into this. Okay, all right. So now let me now introduce the parent function as following. All right. So for the parent function, I'm going to introduce f of x equals 2 minus square root of x. All right. So f of x equals 2 minus square root of x. So at this point, just simply, only at this instant, just simply see this function as a rule. It's a rule. It takes the and the rule of this function says for whatever inputs indicated by the x variable. Okay, the rule says we take the square root of the input and then subtract that from 2. That's the rule of this function. Take the square root. According to the order of operation, we have to take square root, right? Because square root is classified as an exponent. So take the square root of the input first and then subtract that result, okay, from 2. Okay, so that's just the rule. So now, and you have had enough experience in graphing the graph. So for this graph right here, even though, yes, we're learning about transformation, but we don't have to think too fancy yet for a problem like this. Let's just use your own favorite kind of technology and type in this parent function and then instantly pull out a graph. Okay, so let's now look at, so I'm going to show the following. So now think about, I chose my favorite graphing technology to be Desmos here. And you can do the same. You can choose your own favorite graphing technology. A standard TI calculator will work, 83 or 84. Okay? And so once you have input your function, okay, once you have given your function to the calculator, okay, then this is the graph. So I just want to show that, and again, we have learned and clearly understood that any function has a graph that can represent it. Okay, and so this function here that we're seeing on the screen, I mean this graph here we're seeing on the screen is the graph of the function that represents the rule 2 minus square root of x, okay, graphically. So that's just the graph for now, and so we use this, and the reason why I'm drawing that in red ink, because it's I'm going to use the graph of this function here as the parent function, okay, as the parent function. Okay, and then this graph right here, allow me to bring that in the full screen look right here, full screen view right here. So it has a few points that stay right on the grid. Okay, so those points I can use as the guiding points, because with the guiding points it's making it easy. Okay, those guiding points will make it easy to identify the shape of your graph. Okay. All right, so now allow me to put in the guiding points. Okay, so these are the guiding points, and you can see that after putting in the labels right here, they're right on the grid there. So we have 1 at 0, 2, we got 1, 1, and we have another one at the 4, 0, and we have 1 at 9, -1. So these are the guiding points, and that defines that shape. These guiding points define the shape of our graph right here. And you see, this graph may be common for somebody, this graph may be not common for somebody. That's not the point, but my point again is, just say you're given a graph, and now all I'm asking, you can use your favorite graphing device right there and pull out a graph for this instantly. Okay, so that saves you some efforts by constructing table values or anything like that. Okay, so here's the graph, and you don't even need to worry about, is this the transformation of some other graphs? Nope, that's not my intention for this particular instance right here. So we're treating that as a parent function, and we already see the graph right here. Okay, and so now from that way, with the graph here being presented, then I can create the following function. Let's now look at, and I've been using that term, and so now I'll keep calling that here again. And so allow me to actually introduce a few descendants, okay? Because it's just like that same idea that we have learned throughout the previous the discussions on the different elementary transformations. Then we always have a parent, and from the parents there we have the descendant functions. Okay, and so let's look at the first descendants right here. How about I'm going to create a descendant g of x that, as far as the way how it looks, okay, as far as the way how it looks, this g of x is going to be as following. I'm going to define g of x as 2, okay, 2, something same rule with the parents, minus square root, okay, square root, something similar with the parents. See, like I said, the idea about it being a descendants function is that it has to still, doesn't matter how many generations it got passed down, but it still has to have that same, some characteristics, some traits from the earlier ancestor, okay, or from the earlier parents. So 2 minus square root. Here I'm looking at about 2x. All right. So I now define this, and then it's easy to recognize that this descendant here. See, because as I was writing it down, I pointed out along the way that it has that characteristic being exactly the same with its parent. It has that characteristic being a subtraction here, and it also has that square root component. The only difference now is that inside the square root, it takes an expression 2x instead of x, just like that. Okay, and so just for you to pay your attention to that. So, and now we recognize, in that way we recognize, here's how I see it. Okay, so as a relationship with this parent function, it looks like, I mean it really is, g of x came out or is defined as its parent. Okay, because the rule of the parent function is that for every input, we're gonna first take the square root of the input, whatever input that is. Okay, we're gonna take the square root of the input, and then subtract that result from 2. And so here we take there are so many things being involved in this g of x already, but as far as a general rule, I see we take the square root of a 2x, and then whatever that result, we're going to subtract that from 2. And so that means, hey, here I recognize, hey, wait a minute, couldn't that be the 2x here is being the input of the parent function, okay? So this blue version being the dependence, but really it came from the 2x, it came from the parent function that took the 2x expression as its input. Now I make that connection, okay? So now we make that connection right there. And so now, that's just what we observe and notice. And so now let's look at what happens on the graph. Okay, let's look at what happened on the graph. I pointed out that, so here's one descendant. I yelled it out loud, and then I'll just now express through my own thought process and try to make that connection. And I made that connection that, hey, this g of x here came out from its parent function, but instead of taking the usual x here, it's taking a 2x. And so now I want you to look a little further instead before I rush into seeing the graph. So the only difference here is that instead of x, it's an x multiplied with a value c. It's in the form of an ax right here. See, this we kind of generally predict a pattern here. Okay, a generality here that instead of taking the usual input right here, okay, our parent function takes the kind of expression where the usual inputs, but multiply with a coefficient a. And there is still a lot more to talk about that a right there, so I don't want to rush anyone's learning. But so now we just know that we're gonna take 2 times x as the whole expression input, as a whole input expression for this parent function. All right, so now let's investigate the graph right here. Let's investigate the graph. All right, so now I'm going to turn into full view screen right here. And now I'm going to adjust the viewing window a little bit. All right, and so now this is the graph. This is the graph. The blue graph right here is the graph of our, g of x function right here, the descendant function. Okay, so we still don't see anything much. But at least I already see there's that shape right here, that's fundamental shape that's carried over from the parent function, from its parent, if we are treating this blue function here as a descendant function. Okay, and so now let me put in the guiding points right here, and that will make the story become clear. All right, so now these are the guiding points. Okay, so you can see that any of these guiding points that we put in, the first thing that I noticed, and see, I tried to explain that this earlier, and now you're seeing that again. Without putting in the guiding points on the blue, it may be easily confused that this graph right here has gone through a vertical stretch. Okay? If I'm hiding away, that somebody may have already mistaken that this graph is a vertically stretched version of the beginning one right here. All right, but as a matter of fact, it's not, okay? Because if it really was a vertical stretch, let me now hide it away right here. If it really was a vertical stretch, say for example, if we're stretching it by 2 right here, then now notice this point right here, this point, every graph has a certain point where you can click and find out whether it's a vertical stretch or not, vertically stretched or not. So focus right here at that point, that guiding point of the parent function. If the graph if the function we had was a vertically stretched version of the parent function, then here's what it's supposed to happen. All right, there we go. Okay, that's beginning point. That beginning point on the blue version, if it really was a vertical stretch, then it should have been moved up as well. It should have been stretched out, so the point here should be changed to something higher. Okay, but now obviously in our case here, the one that I drew on the board, the real parent function that we're looking at on the board, this is the one that we saw earlier. It still have that same, it still come to that same starting point right here. And then, now once I put a label in, you can notice something. With all of these corresponding guiding points from the parent function, now on the descendant function here, they all stay the same height. They all pretty much stay the same height, but these corresponding points, they come closer to the y-axis. So now that confirmed for me that what I just did here did some scaling. It did some scaling horizontally, but not vertically. All right. And so now after my explanation, and to make it clear that what we've seen here, what we have experienced here is a sideways scaling. And now let's even dive in further and look at that. So on the graph again, now I just explained, if we're looking at these guiding points on the blue graph and compare them with their corresponding parent function guiding points right here, then they seem to be coming closer to the y-axis compared to their parents. Like say this guy right here, this point in blue right here, his parent is here. Okay, this guy in blue, his parent is here. Okay, and any of the descendant points right here comes closer. So that means that this graph here has gone through a sideways, a horizontal compression. Okay, it has been, this graph in blue is the parent function but being horizontally compressed. That's the observation we've made. That's the observation we've made. This graph, this function in blue, okay, written in blue ink and then graphed in blue right there, is the parent. So we notice, algebraically we notice g of x is defined as the function f of x, the parent function that took the input 2 times x, okay? And then now we notice that f of this blue graph compared to the red graph is the compressed version, okay? The horizontally compressed version. Yes, but compression is a horizontal scaling because it happens on a horizontal scale. So I see this as a horizontal scaling, but it's getting narrower. All right, and so we just simply need to write it down, because when it gets to scaling, just like how we study about the vertical scaling, so now when we study the horizontal scaling, we have to take notes carefully and take notes of our observations carefully before we can make conclusions and form into a generalization. Okay, and so now what I notice, so the observation here, as far as the observation, okay, so we saw that this graph right here it's really the graph of f, right? The graph for this g is the graph of f, but being the graph of f being horizontally. The graph of f is horizontally, okay, horizontally compressed. Okay, and but at least it's still pointing in the same direction. It's still pointing in the same direction. So that's all we saw so far. I would like to just hold it right there. Okay, and then the only thing that I would like to point out is that for this 2 right here, it's a value that's positive. Okay, this c right here. Now, this a coefficient currently is positive. That's everything we observe, and this is the observation through the graph. This is what happened in this function that we noticed. That's all. Okay, so now with that, let me now put in another descendant function. Okay, so now let's call that h of x. Okay, so now I'm going to write down. So h of x here, it's another descendant. As I keep making this maybe a joke to somebody, but a parent can have more than one child, right? So we can have many descendants from one function, one parent function. Okay, and so now that's why this is the reason why I have to use a different name here, because it's not the same g that we've had already. We use g for a different name. For a different function. But here, this descendant here, how about 2 minus, okay, square root. So almost exactly the same with that parent function. But this time inside the square root, this text have a minus 2x. Okay, 2 minus square root, instead of x, we had minus 2x. Okay, and so now, very similar experience from the earlier problem. Now this is how I recognize it. You see, we have that square root. Okay, it has all of that components. 2 is part of the rule from the parent's function. Subtract another part of the rule from the parent's function, and it has that square root components from the parent function. The only difference is that this is this minus 2x instead of the usual x. So as I said again, you have learned up to this point, if you have reviewed carefully your composition of function thoroughly, then this is how I recognize it. This is the parent function, but instead of taking the input, x as usual, it's taking some advanced input, being an expression, a minus 2x. That's what I recognize about our descendant function here, g of x. I mean h of x. That's what I recognize about h of x. Okay, and so maybe let me write it a little closer, a little higher up. All right, so this is the parent's function, but taking minus 2x. So it's still in that form. It's still in that form of, instead of being a usual x input, it's going to be now x times with some coefficient. Hey, it changed to a negative coefficient here compared to the earlier descendants, compared to the g descendants that I mentioned earlier. Here is the h descendant. Okay, but generally I see it's in the form of f of ax again. F of ax again. F of ax. F of ax. Okay? Let's now have a look at the graph. And so the graph just now I had was the graph for g of x. So now let's look at the graph for h of x right here. All right, so on the graphing screen right here, this is f of x. Okay, this is f of x. All right, and with a few guiding points right here. And these are the labels. Okay, and this time allow me to zoom it out a little bit. Okay, and I'm going to move the viewing window a little bit for a good purpose. All right, so now let's look at the graph for h of x. So h of x here in blue. This is h of x. Okay. So first thing that caught my attention before I even bring up the guiding points on the blue version, it still has that shape as a halfway, as a sideway, half parabola. But this time, what happened? What seems to be the event that happened here? It got flipped. It got horizontally flipped, treating the y-axis as a mirror. But see, not quite as a mirror here, because it's already kind of upscale. Okay, not quite as a mirror, but it's kind of upscale. So one thing for sure, we saw that it got flipped horizontally. Okay, from the red version pointing to the right, now it's the blue version. From that same starting spot right here, it's pointing to the left. Okay, and now let me put the guiding points in. Okay, so the guiding points now again show that these guiding points stay a lot closer to the y-axis compared to their parent points, compared to the guiding points on the parent function. You see, this point here is supposedly corresponding with that. But look at the x value, it's only a negative 0.5. The distance here is only a 0.5 distance. Okay, this point here compared to 4. So 4 here, it stays 4 grids away. But now on this point here, corresponding to that point, same y value, but the x value comes a lot closer to the y-axis right here. So that point again comes a lot closer compared to this point here. This is x equals 9. This is x equals negative 4.5. Or absolutely speaking, it's only 4.5 grids away. Absolutely speaking, this is only 2 grids away, whereas the parent point stays 4 grids away. All right, so there's still some So we already recognized clearly that there was some flip horizontally. Okay, but then along the way there was still that compression, that sideways compression. The graph got narrower. Okay, so that's the observation again. So let's just document our observation here. So the parent function, I mean the graph of this h of x right here, when we made the graph, then we notice, right? We observe that the graph, this function h of x right here, caused the graph of f of x, right, is horizontally compressed, just like the earlier problem is horizontally compressed. Okay, but now there's something extra. Not only just compressed, because earlier when it was g, it's compressed, but it's still pointing in the same direction. But now it's compressed and, okay, horizontally flipped. All right. So a little more extra added on to that. So we're still having a compression, okay, but it's going to be horizontally flipped. Okay, so that's all the observation for h of x right now. Let's look at another descendant. So now I'm going to define another descendant. All right, so let's now define another descendant here. I'm going to call that j of x. Okay, so j of x here is defined as, how about 2? All right, 2 being the same with the parent function. Minus, okay, just like its parent function. Now square root, and just like the parent function again. Okay, but now it's going to be, how about 1/2 x, so 1/2 times x inside the square root. And so now we've had enough experience through the last two descendants, so I'm not going to take too long to explain, but what I recognize right from here is that j of x, as a descendant, of course, because, and along the way I point out so much the common characteristics with from the parent function. So j of x here is clearly recognized as its parent f, because the rule about 2 minus square root is the rule from the parent. But now instead of square root of x as usual, this is square root of 1/2 x. So now apparently I see that this is the parent function taking the expression 1/2 x as its input instead of the usual x here. Okay, so now we wrote it down. We noticed that, but in the end, so we've seen, g of x was 2x, f of 2x. Okay, h of x earlier, that was f of minus 2x, and then now j of x here is f of 1/2 x. But in the end, we're still looking at putting an ax, okay, putting a coefficient, a linear coefficient multiplied with x, and putting that inside our function, our parent function f of x. All right, and so now once again, let's turn over to the graph and make some observations. Okay, and here again is our graph. This is our graph for just the standard the parent function. All right, just the parent function. And now I am going to look at all right, so this is the graph for j of x right here. All right, so maybe zooming it in, it would be a little better. Okay, I'm zooming it in a little bit. And so again, clearly this is not a vertical compression, because that point still stays at the same seat right here. Okay, and then from that point, everything that seems, and now we'll get it more clear. So now let me put in the guiding points on the blue graph. All right, so now with the guiding points, we can see that it looks like the same parent function. All these y values stay the same, but the blue guiding points on the descendant function here comes farther away from the y-axis. Okay. So in our formal term now, the graph in blue is the graph of f of x that has been horizontally stretched. Okay, so there's a sideways stretch, there's a horizontal stretch going on here in that observation. Okay, because just now I I pointed out what just happened there. Every guiding point here on the blue has a corresponding guiding point that stays back on the parent function, and now what we notice, they all stay at the same height. Okay, but then they come further out. So further out horizontally, that means that refers to the x values. Okay, so they stay further out. And that's why it caused that horizontal stretch. Okay, so now let's write down what we observed. Okay, let's write down our observation. So as far as the observation, so I'm seeing that the graph of J is the graph of f of x. Right? For short, I'm just putting it as one statement. What I see is the graph of f of x. Okay, is horizontally. Is horizontally. So now instead of saying compressed, I'm going to say stretched. It's got pulled out, wider. It got wider. Okay, it's horizontally stretched. All right, it got stretched, and that's it. Now what I mean by that's it is that in the current way how the graph looks, and you're still seeing that on the screen right now. And now let me put that in full view screen right here. The graph in blue is still pointing in the same direction. Same direction. Okay, on the same side of the y-axis with the parent function, with its parent function. Okay, that means my intention, what I'm about to say is there's no flip. There was no flip in this graph that we're seeing. Okay, there's no flip there, and that's why I said, at the end my only observation is the graph of f of x is horizontally stretched. So by default it stays in the same direction, it's on the same side with its parent function. That's what we noticed too. Okay, and so another thing to notice, this 1/2 right here. This 1/2 right here is, yes, it's positive, okay, and it's positive, but it's less than 1. It's a value less than 1. All right, so now, and then we're gonna keep digging in further. Okay, so now let's look at another descendant. How about I'll call that q of x. Okay, and let's define q of x as how about 2. Okay, 2, that same rule from the parents, minus, okay, that same rule again, square root, okay, square root. But now inside of the square root, how about minus 1/2 x right here, minus 1/2 x, minus 1/2 x. Okay. And so now, here's how I recognize it. Comparing this function here with that parent function, f of x, right there. Then I see that q of x here truly is the parent function. Okay? But that takes the input minus 1/2 x. The parent function that takes the inputs minus 1/2 x. Okay, that takes the expression minus 1/2 x as the input for the parent function. Okay, because see, all that rule stays the same, and the rule here specifically the emphasizes that we take square root of the input, because here it has nothing to do with input, so that is always part of the rule. But the rule says the rule has done some taking square root of the inputs. That's the rule of parents, and so now it's still taking inputs. Taking square root of an input, but now the input is no longer a simple x. It's going to be an expression minus 1/2 x, minus 1/2 x. So it looks like this function q of x here is the parent function f of x, but taking the expression minus 1/2 x as its input. Okay, and then in the end, the q of x is still recognized as the parent that takes the inputs ax right here, that takes the the AX expression as its input. Yeah. So 4 descendants at a time, they all have this. They all doing this same thing right here. They're all the parent function, but take the expression a times x, a coefficient times x for its input. Yeah. Okay. And so now I'm going to swing over to the graph again, and let's find out what happened to the graph. Okay. All right. So now here's my graph of the original parent function, and then allow me to again zoom it out. Okay. And then move the viewing window a little bit. All right. So now I'm going to look at. Now let's look at the graph of the Descendants function. All right. And so now keep focusing at that starting points right here. Then I can see that the graph this time points the opposite way. There was some mirror reflection already. Okay, there was some reflection through the y-axis because it's now clearly it's pointed to the opposite way. Okay, that's one thing we observed. And further, what I see now, let me put the guiding points on. Okay, the guiding points on my blue graph here are these points right here. So let's say that point is right on the same spot with its parent point right here, with its guiding point on the parent's function. But then with this point right here is corresponding to that point. But then, so yes, see, it's on the opposite side. That's why it's the negative x value. And further, it's absolutely 2 units away, further away from the y-axis compared to the original guiding point on the parent function. Okay, and then is that the same thing for this other point right here? This other point is minus 8, 0 compared to 4, 0. So same y value. But this point here in blue happens a lot further out. Okay, a lot farther out compared to this point right here on the parent function. Okay, and then I even have to zoom it in, or maybe I'm going to even have to squeeze it out further to all the way to minus 18. This is where I'm seeing the next point, the next guiding point of mine right there, which is 18 square grids away. Okay, just to stay at the y value negative 1. Y value negative 1 on here is only the 9, negative 1. See, y value negative 1 here, it's only 9 grids away, but here it is 18 grids away. All right, it's any of these points is a lot. Any of these points right here is a lot farther out. Okay, so in that way we notice really there are 2 natures. There's a flip. Okay, it's pointing in the opposite way, and there is a stretch, a horizontal stretch. So it's flipped and it got stretched. Okay, so just that's all we need right now. We're gonna write down. We're gonna document the observation. I mean, that's a quality of the thing about yourself is being one of those the earlier generation of mathematicians where you were inventing these, where you were recognizing these, trying to discover these, documenting all of your observations. That's one of the quality that a mathematician is doing. Okay, and so the graph. Looks like getting the graph of this descendant right here is simply the graph of f of x, right? But what has happened to that? What has happened to that? The graph of f of x is horizontally. All right, it's horizontally stretched. All right, so stretch again. All right, it's horizontally stretched, and then. And further flipped. How about, I shouldn't say further, and also horizontally flipped. All right, horizontally flipped. So 2 properties happen. And as a note, what we observed here, this coefficient a in our case here is the negative 1/2. Okay, it's a negative value. Okay, and then its absolute value is less than 1. These are 2 things I noticed right there. Okay, and I could have also mentioned this, the absolute value thing with the a in the earlier function, but we will get all of that down. Okay, we will get all of that down. All right, so now we have experienced enough. We have experimented enough. Okay, the different cases here, and it's now time to put a generalization right here. Okay, so I'm gonna really put back all of the cases there. All right, so now, so as far as the descendants, now this time I'm gonna organize things into a table like this, so that we can recognize a generality. All right, so there were stretch and compress, and of course everything here happens horizontally. Okay, and so let me write this word descendants here a little higher up so that I can maximize my amount of space below that. All right, so these are descendants now. So clearly we're looking at multiple descendants here. So there were graphs that got compressed. Okay, there were graphs that got stretched. We walked through the 4 different descendants right there. So there were graphs that were compressed, and there were graphs that were stretched. So compress happened when it was g of x, that descendants we investigated earlier. That was g of x. Okay, and we define that as, we recognize that as the parent function, but taking the inputs 2x. Okay, and then of course the 2 here with that in that ax form. So any of these descendants came out from the parents taking the inputs ax. Okay, but then we saw a compressed version, a horizontally compressed version, of course, and that here is because the 2 value or the a value here is positive, and further what we noticed here, the absolute value of a was greater than 1. Okay, this is a, absolute value of a was greater than 1. All right, and then we saw another descendant that was also a compression, that was also horizontally compressed. That was h of x. Okay, that was h of x. And h of x was defined as the parent function. Okay, but taking the inputs minus 2x. Okay, so this is a minus 2, that's a. So it's still in that form, f of ax. Right there. All right, so now I see that in this case for h of x, our a value was negative. Okay, but still, here's one thing that's still the same with g of x. The absolute value of a is still a value quantity, a value greater than 1. Double check on that. You can always pause the video and double check this. This is minus 2. So absolute value of minus 2 is 2, still greater than 1. All right, so one common thing between g and h, these 2 descendants. And so now in how I saw that, both of these are compressed. That's why they're in the same column of my table in the way how I'm organizing it. Okay, but then looking a little further than once we look back at what we have experimented, then this g there was no flip. Okay, there was no flip. It stays, the graph stays the same. Okay, but then here it was flipped. H of x was flipped, and when I say flipped, I mean the original parents being flipped through the y-axis. Okay, and now as far as the stretch, we also noted a couple graphs that stretched out horizontally from the parents function. Okay, so which one was that? So that was so we had j of x. Okay, that was defined as, now primarily speaking, that was defined as positive 1/2, f of positive 1/2 x. The parent function that's taking the expression ax for its inputs, but ax here is 1/2. So a is a positive value, okay? And but absolute value of a in this case is actually less than 1. Absolute value of a is less than 1. Okay, well, that's what we noticed just straight out from here. These are just what we draw out, that was what I drew out from what we observed here. Okay, and then here in this case, in that case, we observe no flip. That's why I put it right in this entry of our table. So now I'm in the end, you can see where I'm going. I'm forming it into a table where we can organize these into cases, and then we from there we generalize into a generalization. We put things into a generalization. Okay, we form into a generality like that for that. Okay, and then furthermore, the last one on our investigations, it was q of x that was defined as f of negative 1/2 x. Okay, and then so this one, yes, we just now saw there was a stretch. Okay, it's horizontally stretched, and it got flipped to the other side. That's why I put it here in this corner as well. It got stretched and it got flipped, okay, through the y-axis. So any of these problems, they're all flipped through the y-axis. Okay, so now this is what I further noticed right here. So we wrote down all that observation, but now that's why we had this table. But now I want to pinpoint what's special about these coefficients a right there. So here I'm seeing a is negative value. That's what causes flip. So that's why now, at least in the same row for all of those functions who flipped, who came out from the original parents but got flipped away, the a here is negative. All right, and then absolute value of a in this case is less than 1. So now you can start seeing for those who are put in the same column, for those functions, those descendants who are put in the same column, at least their absolute value of a is common. And common, I mean they're not the same absolute value of a, but they're common in a sense that they're less than 1. That's stretched, for stretch. Absolute value of a here is going to be greater than 1, corresponding to, it's a horizontal compressed right there. Okay, so this table is kind of regulates that generality already, okay, if you want to stay with that table. But then, of course, let's now give a formal, let's give it a formal worded generalization of all of these rules right here. Okay, and so see, I call all of these the horizontal scaling, because it's all about there's some scale that's multiplied to that, and it adjusts the scales on your graph. It's narrower, it's wider, okay, or it's flipped the other way. There's always some scaling happening there, but the kind of scaling here is scaling on the horizontal axis, and that's why I categorize all of these here as horizontal scalings, okay, the different horizontal scalings. And there could be both in one case. All right, so now let's head over to this board over here, and let's write down the general rule. Okay, so I'm going to start out with, so for horizontal scaling, I'm going to say let f of x, okay, be a parent function, okay? Just any parent function. And then from there we're going to define some descendant function, g of x, to be f of x, okay, but takes ax, a coefficient times x, okay, takes that expression as the input. All right, so in that case, in that way right here, okay, so this function g will have the graph, okay, so has a, so the function g defined in this way right here has the graph of f of x, okay, because it's a descendant, so it makes perfect sense. It makes perfect sense that it has all of its characteristics from its parent, okay, but now it's gonna have to be slightly different. Okay, so this g has the graph of f of x, okay, that's, but horizontally scaled, as following. Okay, so there are different ways of scaling. Okay, horizontally scale as following. So now I'm going to write it down right here. All right, so it's going to be a horizontal. It's going to be horizontally compressed. Okay, it's going to be horizontally compressed. Okay, and now I'm going to get even more precise, and I'll get back and explain that. It's going to be horizontally compressed by absolute value of 1 over A. Okay, if absolute value of A is greater than 1. All right. So I added in this extra information over here to be even more precise about how far it's gonna, how far it gets compressed in. Okay, and it's compressed by a factor. Really, this means a factor. Okay, of 1 absolute value of 1 over A. Okay, but then it's a compression. It's a horizontal compression, as we have already noticed, if the absolute value of A is greater than 1. Okay, and so that is just what I wrote on this chart right here. Anytime the absolute value of A is greater than 1, absolute value of A is greater than 1, the function, the parent function gets compressed horizontally. And that's the case right there. Okay? And further, and flipped, okay? And flipped, or horizontally flipped. How about I'll say, and also horizontally flipped. So this is sort of like extra additional, extra details on that. Horizontally flipped if, okay, A itself is negative. All right, so that's really one case here. It becomes a compression, a horizontal compression, and compressed by a factor of absolute value of 1 over A. Okay, if that was the case, if absolute value of A is greater than 1, and then further, or also it's going to have it at the same time. If this happens, if absolute value of A is if A is a negative value, then it's going to get flipped, okay, horizontally. Okay, and so in the next case right here, so this is one case. It's going to have the graph of f of x horizontally has the graph f of x is horizontally scaled as horizontally. It's going to be horizontally stretched, okay, and stretched by, when it's stretched, it's also going to stretch by absolute value of 1 over A. So this part right here is a little, it's not so clear right now. I will explain all of that. Okay, stretched by absolute value of 1 over A if A itself in absolute value is less than 1. Okay, it's less than 1, and it also becomes horizontally flipped. Okay, if A is negative. All right, so in any case, if A is negative, it's going to flip the graph. All right, so anytime we have a negative A, flip the graph. Flip the graph on the side way. All right, so that's the generalization of all the horizontal scalings right here. So this is the worded version, okay, and this is the compressed version. This is the the condensed version where things are organized in table right here, okay. And so I can also add in that detailed information that I put it down earlier. So we we compressed or we stretched by a factor of absolute value of 1 over a. Okay, by absolute value of 1 over a. Okay, absolute value of 1 over a. It's all that scaling factor right there, 1 over a. So it can be quite important. Sometimes you get that. So let me demonstrate by let me come back to the graphic there and demonstrate what it means by 1 over a. Okay, absolute value of 1 over a. So now this is the graph of the original parent function through my demonstration. Okay, and let's look back at g of x. Let's look back at g of x. Okay, I'll just pick it randomly. So this is the graph for g of x, and these are the guiding points right here. All right, so compressed now, I'm trying to explain by what it means. I'm trying to explain what it means by compressed by absolute value of 1 over a. So g of x here as a definition, it was, according to our function, g of x was 2x. This is a right here, the actual a. Okay, so absolute value of 1 over a is going to be a 1/2, a positive 1/2. That's what it is for this case. Absolute value of 1/2. Okay, so now let's look at that. How do we see that in the graph right here? Absolute value of 1 over 2 in this case. See, that's why every point here on the x-axis, it's get halved down. That's why in my explanation earlier, I was trying to explain that these points came closer. So came closer by how far? It came closer by, see, in this case particularly, it's half of the distance compared to the x values on the parent function. Okay, so why is it half here? Why is it half here? Because it's because it's absolute value of 1 over 2. Okay, it's absolute value of 1 over 2. Because this g right here was g of x equals f of 2x. F of 2x. G is defined as f of 2x. So absolute value of 1 over 2. And that's the factor. Okay, that's why it's so we always put that factor, that scaling factor. This is, I wrote that now in red, it's a scaling factor. Okay, it's scaled by absolute value of 1 over a. That's how much it's, so think about the distance from the parent's point, okay, then it's going to get half down or it's going to get a quarter down. It all depends on that factor. So if this is a 4 here, it's going to get scaled by a 1/4. Okay, so in that way, now back on the graph of the original function. Okay, now let's look at q of x. All right, so this is the graph of q of x. All right, and now these are the guiding points on the q of x. Okay, so the original parent function guiding points here, say for example that point right here, it's at x equals 1, but this point here is x equals 2. I mean x equals -2. Okay, so that means it's double. It's double. You see that it's double the distance right there. Here it's only 4, okay, but here it's double. So why is it double here? It's double because it's being scaled. It's being scaled by a factor of absolute value 1 over a again. So a in this case is a -1/2. Okay. A in this case is a -1/2. So 1 over -1/2 is a -2, but in absolute value. That's why it's a +2, and that makes it double all of the x value distance. All right. And so that's the idea. And so now after I pointed it out and in precise scaling and all that, and either we're reading the table version, okay, or we're reading the formal worded generalization here. Either one of the cases, I mean either one of the approach is, when it gets to practical situation, when we're doing it, when we actually apply these, it's going to be extremely hard because there are so much details. There are just simply way too much detail. I even sense, in my own personal experience, I even sense that getting the horizontal scaling is a lot more details than the vertical scaling. Okay, and so just like the earlier cases, just like the earlier elementary transformations, I picked up advices here and there, so I came to this advice that I picked it up from my professor back there, and now I'm handing it down right here so that it will hopefully help. It becomes just like a one statement, but it guarantees you will always put your horizontal scaling in the proper place right there. Okay, instead of worrying too much, because there are too many details. Even though I wrote on a table version like this, there are way too much detail. We got to keep track of positive A or negative A. Okay, we got to keep track of absolute value A being greater than 1 or not. Okay, greater than 1 or less than 1 for absolute value A. And we also have to keep track of absolute value of 1 over A to know how far it's stretched out or how close how far it got compressed in. Way too much details. So yes, this is good. This is okay for anyone who have been doing math for years, like my case here. I've been done that for years. So looking at a table like this, I'm okay. But when I was starting with this, I had to struggle as well. Okay, so for students who are starting in with this is not a good recommendation to get to crank right into this. And A is positive, absolute value A is greater than 1, A is negative, absolute value of A is positive, it's greater than 1, way too much information. Okay, so allow me now to show this advisor here. So we had all of that, the worded generalization, but I'm going to erase that. Okay, to just write down a general advice, because any of this comes into just one statement. And then this only one statement, we do not need to worry about. We can completely let go about. All of that. Keeping track of all of that. Positive A or negative A, or A is absolute value A greater than 1, or absolute value B of A is less than 1, or absolute value of 1 over A. How big is that? We can let go of all of that. Okay, because this is how. And so one statement of the advice here. So anytime we are doing this horizontal stretch, okay, for g of x, that's defined as f of ax. This time A is so special, allow me to write it in red ink. Okay, if we have any function g of x that's defined as some known function f, some parent function that takes the input ax right here, then simply this is what will happen to the graph right here. To create the correct transformation, this is what we do, which is simply multiply. Okay, we're going to multiply every x value. Okay, we're going to multiply every x value by the only one surprise, by 1 over a. We multiply every x value by 1 over a. Okay, that's all there is. We multiply every x value by 1 over a. So a can be positive, a can be negative, a can be a value greater than 1, a can be a value less than 1. Absolute value of a can be greater than 1, absolute value of a can be less than 1, doesn't matter. Just multiply every x value by 1 over a. That will guarantee you land your point into the correct place on the transformed version of the graph. Okay, and then that will get you successfully drawn the graph, provided you already know the shape of the graph from the known parent function. All right. All right, so now we are ready for heading into example number 7. Okay, and to apply our understanding into some actual hand sketch graph, doing some actual hand sketch graph of a function as a transformation. Okay, so allow me now to write down the worded instruction of the problem. So now I'm going to say let f of x be represented by the given graph. All right. So now again, let me pull up the given graph here. That is the graph. Okay, so this is the given graph. And then so now once we have that graph given, the goal once we're seeing that graph, and so the idea now is for throughout the entire example 7. So I will be using this same the graph, and we will be having different problems where each function is going to be a transformation out of that particular graph right here. So again, it's very similar to the earlier problem, the earlier examples, again in a sense that we don't have to worry about what kind of function, what rule specifically gives this graph representation. Okay, but all we have to do is, hey, we already had a function, it has a graphical representation here. What's going to happen if we have a g of x equals this and g of x equals that as a transformation on this given graph? Okay, and so allow me to further complete my worded instruction of the example. Okay, so now we want to sketch. Okay, sketch the following graph of the given each given function as a transformation of f of x. All right, and so I may change the wording slightly a little bit compared from with the wording in the earlier example problems, but it shouldn't change the overall structure of this particular kind of problem right here. The idea now is that we already had that graph given, and then I'm going to be given out a function g of x, and then we want to recognize that function as a transformation of f of x and use that to make a hand sketch. Okay, so we already had technology to give us that graph here that you're seeing on the screen right there, but now for the one I'm about to give right here, we definitely want to stay with paper and pencil. Okay, because we don't want to completely build things from table values, and that's going to make it really hard right there. And besides, we don't know the rule. The rule is only whatever that's represented by this graph, but we don't know a specific rule. So building a table of values from scratch is completely impossible for this kind of problem. That's why for any function that's about to be given here, we want to see the function as a transformation of this given f of x through the graph right here. Okay. And so now with all that, let's look at part A. Let's graph the function g of x. Okay, let's graph g of x. That's defined as f of 4x. Okay, f of 4x. All right. So immediately I recognize that this is in the form of f of ax right here. And so we know that we're going to be running. So this is a good sign that rings a bell for us about we are going to have a horizontal scaling. Okay? Because this function g is defined in a way that from its parent function, it's taking an expression 4x, okay, to be its input instead of the usual x. Okay? So that's what it is. And so now let's make some further observations regarding this definition, regarding this function g right here. So I see that a is a positive value. Okay, I see that a is a positive value. I see that a equals 4, which is in this case right here, absolute value of a equals absolute value of 4, which is a value greater than 1. Okay, so we got some further information right there. Okay, and so now with all that information, so as an expectation, okay, as an expectation, what's expected here is that, so having a positive a, if we look back into that table that I've had throughout the detailed explanations right here, then as an expectation, I expected, or it is expected that we have no flip. Okay, so there's no flip. That's one thing. So it's making things easy a little bit there, but and then this thing here is going to be a horizontal. Okay, or horizontal compression. Okay, and then it should be compressed by a horizontal compression by a factor of absolute value of 1/4 right here. Okay, so it's compressed by that much, which is compressed by 1/4. But precisely how do we do this? Okay, so this is just an expectation right here, but precisely speaking, how do we transform, how do we translate this understanding of ours in a thought right here into an actual work so that we can do that on paper and pencil. And that's what matters. All right, and so now in that way, allow me to, well, first of all, before I move to the other board right there, let's look at the guiding points of this current graph right here. So this current graph has these guiding points right there, okay? That defines the shape. So technically I don't have to put a point here, but I figure we put a point there to make it clear that there's a line pattern here, and it's going as a 45 degrees for now. Okay, so this point here is there in the original parents function. So now with the labels being displayed here, we got the coordinates being displayed here. Okay, and so now let's get into my other board. So now it becomes handy to have this advice that I pointed out earlier, because information that we extracted from that table earlier, even though it's already an organized table, but it's still a lot of information. So in order to successfully create the graph for g of x, all we have to do is multiply every x value by 1 over a. Every x value of the original parent function. Okay, so we're going to multiply every x value by 1 over a. So it's that a right there. All right, so that's one advice right there. And now with the graph is being on the screen right now at the same time, you can see that if we really attempt to multiply every x value, it's impossible, because it's a whole trace of all points. And that's the reason why we stay focused right on those what I so-called the guiding points. Because once we stay on those guiding points and do the proper work here, do the proper transformation here on every guiding point, then the graph is gonna fall out accordingly. Okay, and that's the whole purpose of using guiding points. So guiding points, again, it's just my own personal approach right there, and I would like to pass it down to my students. Okay, so now I'm gonna multiply x here consequently to every guiding point on this graph that we're seeing. So let's now make a table. So on this table, okay, f of x, the original graph in red right here, I have the first point being at minus 6, 0. Okay, I have another one at negative 2, all right, 4. All right, and you can read the graph along the way with me as I'm nailing down these points on my table right there. I have another point, and I may have to make this table longer into another one to continue with this. All right, and then now my third point here is going to be a negative 1, 1, and I also have a guiding point at 0, 0. That peak that hits that bottom peak that hits the x-axis. And then now I'm running out of space in my table. I'm going to have to draw the continuation of my table. So it's still the f of x column here, being continued from this column. Okay, so I have the next point over, I have a 1, 1. Okay, and the next point over, I have a 2, 4. The next point over, I have a 3, 3. Okay, and the next point over, I have a 5, 5. All right, 5, 5. So now applying this advice here, at least to every x values on this set of guiding points of our current graph, it will get us a successful work right here. So we don't have to use this advice for every point, because literally it's impossible. Okay, so now this is how I'm going to create my g of x, which is defined as f of 4x. Okay, so this is the column. This column contains all those guiding points on the blue graph here, f of 4x. All right, so now The advice only says multiply every x value by 1 over a. Our a value, as I sketched it down on the other board earlier, our a value is 4. Okay, it's positive. Its absolute value is greater than 1. Okay, that's all we need. But then, now when we're actually getting into doing it, all right, so here we go. We never have to worry about, when for this kind of work, we don't have to worry about the y value. So for the first pair, y value stays the same, 0. Okay, but x value must be multiplied by 1 over a. So this is 1/4. So 1/4 times a 1/6. I mean 1/4 times a -6. 1/4 times a -6 gives me a -6/4, which reduces down to a -3/2, or -1.5 right there. Okay. The next point right here, -2, 4. Y value stays the same because this advice only apply to the x values. So now, 4 stays the same. That's the y value. Now, -2 times a 1/4. -2 times 1/4 gives me a -2/4, a -2/4. Okay, or reduce down to a -1/2. -1/2. All right. -1, 1. This y value stays the same. And then -1 multiplied by 1/4 gives me a -1/4. And this fraction is already irreducible. Okay, and in its lowest term. So now 0, 0. The y value stays the same. Okay, but 0 times 1/4, it's a 1/4. So I just multiply as is with that 1 over a factor without worrying about the sign, and then whatever the sign, it will come out accordingly. So see here, I just simply multiply 1/4 to every x value. Okay, and so now I can start picking up pace a little bit. So now for this pair right here, it becomes, okay, 1 of course, but this is a positive 1/4 still. Okay, now that is a 2/4 or a 1/2 for x, okay, 4 for y. That here is going to be 3 as a y value. It stays the same. This x value multiplied with 1/4 gives me a 3/4. And so it is extremely crucial that you are fluent. Whoever viewing this lesson is, you are fluent with working with fractions. I mean, it's an essential skill that at this point when you're in pre-calculus, it's a must that you are working fluently with fractions. 5, 5. So I have the y value 5 stays the same, but the x value being 5 originally, now it becomes 5/4. Okay. So these are all the points right there. So now I'm going to bring these points, right, onto the actual graph, because now we have a clear guidance right here. Because we can draw the graphs through these points, and that's going to make our shape of the graph. All right, that's why I've been calling these points the guiding points. All right. So now on the graph. All right, so now on the graph, these are the guiding points in blue. All right, so there they are in blue. Okay, allow me to zoom it in a little more so that we can see it better, and then it's also appropriate to, it's also good to later on put in the labels right there. Okay, so now I'm going to show the labels. All right, just to make sure that these points are consistent with what reads in our table. Okay, but now since having the labels here is a little too much for the screen right there, I'm going to just take the labels out. But when we can double check from the left to the right, we got that point here being a -1.5, just consistent with what's on the table. So let me show the original board with the table again. Okay, so with these points right here, they look to be consistent with what's on this table that we have. All right, so we can always double check. And so now I expect that there's no flip. There was no flip. So I expect that there's a shape that's going up here, rising up as a line, okay, and going through these points here as a parabolic shape, and then hits down, swing down to that point as in a straight line, just like that, okay, and swing up. All right, so in that way, now here it goes. Here's how we graphing it. Okay, so now just really trying to mimic as closely as possible to the actual hand sketching work right here, then this is how it works. Okay, so I'm drawing through as a straight line. All right, through those and now parabolically through those points, and now connect straight down and connect straight up. All right, and that's how we created the graph of this being recognized as a transformation from that f of x right there. So g of x equals 4x. G of x equals 4x. All right. And let's now look at another example. So now I am going to give another function. And now these are we're all indicated by different problems, so allow me to reuse the name right here. So it's g of x again. Okay. So now part B of the problem. Let's look at g of x. That's defined as f of negative 2/3 of x. All right. And so now this is again the graph of the original parents function. So I see this function here is in the form of f times ax. So clearly speaking, it rings a bell for us that we're going to have some horizontal scaling being done here, being applied here as a transformation here to the original graph of the parent function. And then furthermore, I recognize that a is negative 2/3, that value right there. Okay, I see further that a is negative, okay, due to that minus sign right there. So we expect some flip, okay, some flip through the y-axis. Now furthermore, absolute value of a in this case is a absolute value of minus 2/3, which is 2/3. Which is clearly a 2/3 being less than 1. Okay, so I'm expecting here that we're going to have to horizontally stretch out our graph right there. Okay, so I'm just going to note down the expectation here. So it is expected, okay, we're expected, or the graph here is expected to, okay, it's going to be flipped, okay, we're going to flip it horizontally. All right, and then we're going to have it stretched horizontally. All right, so those are the expectations. But once again, now that we have all of these expectations, it's not that simple to put it in, especially when it comes to precise scale right there. Okay, because yes, we're gonna stretch horizontally by the scale of absolute value of 1 over the minus 2/3, okay? That's to be precise, which is now a scale by 3/2. Absolutely, okay? That's a lot of information, way too much information, okay? So in that way, now let's stay back, and this is the reason why in any of these examples, I just want to point out how useful that advice came out for us. And once we blend it together with using the idea of guiding points right here, it's going to become extremely useful. Okay, so now I'm going to erase out this column of my table, but I'm still going to retain the column that lists down the original guiding points. All right, so here we go. So now when it gets to really doing it right on our guiding pointer here, or to any value, any point on the graph, all we have to do is just multiply every x value by that factor 1 over a. So our factor a here in this case is a negative 2/3. Okay, so keep that in mind. Save me from keep swinging back and forth between the two boards right there. Okay, so g of x. Okay, that's defined as f of minus 2/3 x. Okay, g of x defined as f of minus 2/3 x. Okay. So now I am going to multiply every x values, and we have had this done with this similar experience from earlier problems, so allow me to start picking up pace a little bit. First pair of value, y value stays the same. So comma 0 here, comma 0, comma 0. But negative 6 now is multiplied with, so 1 over a, really 1 over a in this case is just 1 over minus 2/3. We don't have to worry about absolute value or anything like that. But then 1 over minus 2/3 really is a negative 3/2. That's what we're going to multiply. So negative 3/2 is what we're going to multiply for every x value. Okay, so negative 3/2. So now minus 6 times negative 3/2. Well, the math is now coming easy. It's giving us positive 9. Okay, so when we stick with this advice, we don't have to worry about absolute value or anything like that. And the operation here will land us into the correct point value, and then it will show the compression or the stretch, okay, or the flip, okay, if there is any. All right, so now minus 6 times negative 3/2, that lands us into a positive 9. All right, so now I'm really going to pick up pace right here. So that next point right here, minus 2 comma 4 stays the same, okay, but minus 2 times negative 3/2, that gives me a positive 3. Okay, now this next point here, comma 1 stays the same because it's y value. This one right here is negative 1 times negative 3/2, positive 3/2. Okay, so now, and that next point here, needless to say, it stays 0 comma 0 because x equals 0 times negative 3/2, it's going to be a 0 again. Now, continuing with that table on that next point on the graph right here, on the parents function, 1 comma 1. So comma 1 for the y value, still there, but now it's going to become a minus 3/2 for the x value because 1 times negative 3/2. Okay, now 2 comma 4, so 4 stays the same because it's x value, but the 2 right here is going to get multiplied by negative 3/2. That gives me negative 3. Okay, negative 3, and then negative 3, and then now 3 comma 3, that y value stays the same. 3 times negative 3/2 is going to be a negative 9/2. Okay, 9/2. All right, and now 5 comma 5 is going to give me, right, so the y value 5 stays the same. Now 5 times negative 3/2 gives me negative 15/2. Okay, and negative 15/2 is about a 7.5. Okay, negative 7.5. And this is a negative 4.5, and so on and so on. If anyone really loved thinking as a decimal, in terms of the numerically in terms of the decimals. All right, but now we have enough information now to put down our updated guiding points in blue, and then through those points we're going to be able to see the graphs. Okay, so now I'm going to swing into the graph right here. All right, and then let's now have a look. So with this graph right here, as I have mentioned earlier, we expected some flip horizontally. Okay, so that means in the shape right here, fundamentally, I am expected that the end result, you see that zigzag part right here of the graph, that zigzag portion of the graph, it should be on this side, and this sideway parabola is not much to be noticed with the flip, but then this line going up right here now will become a line going down this way on the opposite side because it flipped. Okay, that's the idea. All right, so but now whatever we're saying, just once we put on the guiding points, it will help tremendously. Okay, so now these are the guiding points. All right, these are the guiding points. So just like that, I already noticed there's some kind of these points are here form into some parabolic shape right there, and at this point it's a good idea that I can zoom it out a little bit more. All right, so I'm continuing to zoom it out, so now that shows enough. Okay, because earlier when the zoom was too close and I couldn't point out all of the guiding points that we have. 1, 2, 3, 4, 5, 6, 7, and 8 guiding points all total. You see, so now I can sense that this graph goes like that, going up, just like this piece going up, but now it's on the opposite side, it's going up, drawing down as a parabola, swinging down as a parabola hits to that valley or that bottom peak, and then now it has that zigzag shape right here. But we do have now a sense about stretched out things out a little bit horizontally. So now let's get ready for sketching that graph. But when we're actually sketching it, it's just the way how we're doing things. We're going to sketch from the left to the right. We're going to draw from the left to the right. Okay, so here we go. So now I'm going to draw that. Okay, and you can see that with papers and pencil. Okay, that's going to happen like that. So these two are straight segments. And of course it should start all the way out there, but there's no need to. Okay, because any paper will be limited anyway. And now it's going to swing down in a parabolic shape right there. Okay, and now it's going to come out as a straight line. But see, these lines in blue right now, they are no longer in 1-to-1 scale anymore. Versus this, it was 1-to-1, but now it's no longer 1-to-1. It changed the slopes here and all that. But see, this line is supposedly corresponding with this as a transformation. And then this zigzag right here is corresponding to the red shape right here as a zigzag. All right. And that is how we have sketched the graph of g of x. I try to stay close as much as possible as we were doing that really with paper and pencil right there. And that was the graph of g of x defined as f of minus 2/3 right there. So we saw a flip just like what the expectation here was, and we saw a stretch. And we stretch with that. See, what's really got a lot of students struggle with is the scaling. How big is the scaling right there? And if we're doing this, it's going to be hard. So that's why I stay with that advice right there. All right. And so now, before I'm leaving the example here, let's have an FYT for everybody to have an opportunity. Whoever is learning from this video lesson, let's have an opportunity to give it a try on your own. Okay. So now, let's look at this FYT problem. So how about as an FYT, I want anyone learning in this lesson to try the following. How about we're going to sketch g of x as f of negative 1/3 x. All right. And once again, we're still constructing this graph, sketching this graph as a transformation from the given graph right there that's given in the picture. So allow me to once again pull out the graph again. All right, so this is the graph of that. Okay, so now go ahead and pause the video. Okay, get your own thoughts and lay down your thought process and then go through the guiding points right there. Okay, and I can also put the graphs here in close view again. So this is the graph for f of x in full screen view right here, so that you can take complete notes of all of these guiding points. All right, so at this point, after you have already had your own the sketch right there, hopefully you have paused the video and spent enough amount of time right there. Okay, and there's no need to rush. Take as much time as you can to get your skill fluent. Okay, but now let me just simply, and it's an FYT, so I am not going to show as much step anymore and as much reasonings anymore. I'm just going to show the final answer. Okay, so what I recognized here is that our A is a negative 1/3. And this thing here, it's in the form of an f of ax right here. So it rings a bell again about we're going to have a horizontal stretch, okay? I mean a horizontal scaling. But now, is that a stretch or a compress, or that I leave that for your expectation right there, and you already had the graph at this point supposedly. Okay, so now with this information, now I'm going to show the final graph as the end result right here. Now this is our graph of the original parents function. Now this is the graph of the descendant function right here. All right. And I can just complete it out a little more. All right, so that in quite a far zoom view right there. All right, so, and now let me show these guiding points right here. So these are the guiding points for us. Okay. And I really have to zoom it out in some pretty good extreme zoom like that. All right, but that is the graph of our function g of x right here in blue color, and it has all of those transform points like that, and I can even pull it out even a little more so that it can show completely all of these guided points like that with labels. All right. All right, and so now we're heading into example 8 for another class of problems right here. Okay, so now let me spend some time writing down the worded instruction of the example. So here we are at example 8. All right, so I want to sketch the graph of the given function. By recognizing it as a transformation of a known function. All right, and so this example 8 here, the problems about to be introduced in this example 8 are going to be similar to those problems that have been introduced in a few examples earlier. The idea now is that we want to, so we are going to be given a function, and then we want to sketch the graph. So we're doing this on paper and pencil. We are not going to use technology to get it through and construct a table of values. That's not what we're doing here, but then we're going to sketch the graph by recognizing the function as a transformation of a known function. Okay, so I have to be specific here a little bit. I have to be clear a little bit here, but recognizing it as a transformation. Okay, so we want to recognize the function given as a transformation of a known function. Okay, so we want to, that's one thing to understand, and we want to recognize that as a transformation of a known function. Okay, so now let's get ready for our first one here. So now I'm looking at, how about, let's look at g of x, okay, to be absolute value of 1/2 x. All right, absolute value of 1/2 x. And so this is our function given right here. We want to sketch the graph. But again, as what I was saying, in what I was saying earlier, we don't want to get directly into, x equals 0 gives y equals 0, x equals 1 gives y equals, etc., etc. We don't want to build table of values from scratch just to construct the graph. And the worst thing is we don't want to just immediately give it to a calculator, a graphing calculator, and pull out a graph. Then in that way, you will lose all that sense about connecting the understanding clearly about the function itself. So here we want to recognize. So the idea now is that if this function was a descendant function from a known parent function, our first thing is to recognize what the known parent function is. And so that's why, like as I said, we have seen this kind of problem before. Okay, so in what I'm seeing here right now, we got absolute value. We have absolute value, and then inside of the absolute value, there's a 1/2 x expression. All right, so that immediately rings a bell for us that, hey, we have seen this function. We have seen this function. F of x equals absolute value of x. And this function was introduced back at the lecture where I introduced about the toolkit function. So this is indeed one among the toolkit functions right here. All right, and so with this function known, and the reason now I see this is a known function, because we have seen that in the toolkit functions. Okay, but now upon knowing this function right here, how is this function g of x connected with f of x? Okay, and so now I see algebraically g of x here is this, because in the way how it looks right here, then f of x is almost identically the same with g of x, because we have absolute value. The only thing now is that the rule for f of x says for every input, we take the absolute value of that input. And so here, it seems like we just substitute 1/2 x for every input of f of x, and that's how we're ending out with 1/2 x right here. And now I'm more firm that g of x here is related with f of x by this rule. It's f of 1/2 x. All right, so now this is what I mean by we recognize this function g of x, given here as a transformation. Okay, so by the way, what transformation is this? So now we're in the form of a function, the parent function f being taking the input as an expression ax right here. So that now perfectly rings a bell that the transformation we have here is a transformation where it's going to have a horizontal scaling, okay, because of that ax form right there. All right, so now we're going to be all clear with that. So now just like what I did back in example 7, then you can see that so a in our case here is a 1/2. It's a positive value, okay, and absolute value of a, okay, is less than 1. Okay, so that's all of that information right there. Okay, so that means we can draw out a couple conclusions, a couple expected feature of g of x already. Okay, we can draw out a couple expectations about the graph of g of x. So the graph of g of x, first of all, it's a positive a, so no flip. Okay, no flip. And then, so now with that absolute value of the coefficient a being less than 1, then I'm expecting it's going to be a stretch. Okay. It's stretched horizontally. All right, horizontally. Okay, so these are just simply what's expected. Okay, so any of these two right here. Okay, but in the end, again, throwing in these expectations right here is not helping much in terms of sketching the actual graph, because when it gets to the practical side where we have to sit down and doing that on a paper and pencil, it's not that easy. Okay, and so again, that is the reason why the advice I've had up here will always be the life-saving situation right here. So this is the advice. So now with the advice, all we need now is for every x value, we are going to multiply every x value by 1/a. Okay, and I have already just now indicated our our a value of this particular transformation right here. Okay, so and then just like earlier examples, all we need to do now is that instead of multiplying really every x value, we're just going to focus on a few guided points or guiding points on the parent's graph like that, on the parent's function. Okay, so in that way, let's look back at the graphing screen right here. So now with my graphing device right here, I only use this as a way to show the graph of the parent function. So let's now look at the parent function. All right, so here it is. This is the parent function, and the reason I said it's a known function because we have seen it before. So this graph right here is the graph for this parent function. Okay, in red ink. This one right here is the parent function. It has that graph as seen here. And so now, in this way right here, I'm going to put in a few guided points. And so the guided points are just simply are simply chosen by those easy points, by those points that we can easily recognize being right on the grid right here. So I'm having a few. All right, so these are a few guided points that I can see. Okay, and then as the very original version of the parent function right here, this is a V shape, a 90-degree the angle that stays right at the origin of the graphing space right here. Okay, and these are the guiding points with the labels on top of that. All right, so now once we have had these guiding points successfully labeled in, okay, we are now ready to move to the other space of the board and then construct that table of the guiding point values. So it's not the table of values that we use to construct a graph. It's the table of values where I'm listing down all the guiding points and see how we can adjust those x and y values of the guiding points to create the updated version of the graph. That's what we have been doing throughout the whole time. Okay, so now I'm going to put the graph in with the other board right there. All right, so now I'm going to create a table, okay, and here's f of x. So the original graph for f of x has the following points. We have negative 2, 2, negative 1, 1. We have 0, 0. We have 1, 1. And we have another one here being 2, 2. Okay, so these are the guiding points on the red original parent function. Okay, and now let's update these guiding points here on the blue version. So the blue version here as a descendant, okay, that is f of 1/2 x. That's what we recognized, and we still have this on the other board right there. Okay, let me quickly swing back. That's what we recognize. Okay, so g of x is related with f of x as that f of 1/2 x. So our a value is this positive 1/2 right here. Okay. And so now in that way, 1 over a is simply just 1 over, let's do a quick little math right here. 1 over a is going to be the same as 1 over 1/2. Okay, 1 over 1/2. And that means the math here comes out quickly to be 2, positive 2. So now this advice says that we're going to multiply every x value by 1 over a. So these are all the x values that we need to focus to. Technically we have to do this for every x value on the trace that created that graph, but now we can just simply focus on this particular one. All right, so in that way, first pair of values, negative 2, 2, that y value stays the same because this advice did not have anything to do with the y value, so the y value stays the same. But now the x value here, negative 2 times 2, that gives me negative 4. So now this point is now transformed into this point right here. Okay, so it's not the table of values that we've been doing as to construct the graph from scratch, but the table of values to show the transformation from the previous guiding points to another guiding point right here. Okay, and then now for the next pair of values, this point at negative 1, 1 on the original parent function is now transformed into, okay, so 1 for y remains the same. Okay, but negative 1 for y is transformed to negative 2. All right, because negative 1 times 2, that gives me negative 2. All right, and so now we can start picking up pace right here. So the next pair of value is transformed into 0, 0, because 0 times 2 is 0. This y value stays the same. The next point here at 1, 1 originally is now transformed into negative 2, 1. Okay, and that's simply because 1 times negative 2 for the x value gives me negative 2 here. 1 times 2. That's my error right there. So now, forgive me that I just have to correct that. So 1 times 2. Okay, so 1 times 2 equals 2. But this value 1 for the y value stays the same. All right, and then the next one here, 2, 2. So x value, y value. So now it's transformed to 4, 2. All right, so this now completes our table of transformation. Okay, for all of the guiding points on the transform function on that descendant function g of x right there. All right, and so now let's now put all of those on the graph. All right, so now the transformed guiding points as the blue versions right here is here. Okay, and they are all with the labels right here. So let me zoom that in a little more so that we can see how to point. So once again, if we are checking, then they all stay at the same y value with their parent points, but they are being changed in the x value. So in this case right here, we expected a horizontal stretch as concluded earlier in this. So we had a stretch. We had a stretch horizontally, and so in that way right here, you can see that on the graph right here, all the blue point being appeared further out away from the y-axis compared to the parent version. Okay, so in that way, now we can put the actual graph in. And so now with these guiding points right here, now we are ready to draw the graph. And so the shape here has to be maintained, this V shape, but now the V shape in blue that we're about to draw must be wider, okay, horizontally. So now this is what it looks like. All right, so one piece is going down like that, and the other piece is going up. All right, and that is how we draw and we sketch the graph of so this graph in blue right here is the graph for this function, g of x equals absolute value of 1/2 times x. So 1/2 times x is inside of the absolute value. All right, and so that's one of the examples where we try to graph a given function by recognizing it as a transformation. So the transformation, and the only transformation we saw so far is that transformation that transformation where we horizontally scale that by stretching it horizontally. Okay, let's now look at another one. All right, so now for part B of the example here, let's look at how about g of x equals let's do square root of x. Square root of minus 2x. Okay, square root of minus 2x. Square root of minus 2x. All right, so let's now get into graphing it. Okay, and so just from the look of this function, and we're trying to recognize. So here's the thought process. I see square root. Okay, and so I search within my memory. Where have we seen square root before? So square root is one of this simple square root function is one among the toolkit functions that we have learned before. All right, so now clearly speaking, this is a known function. Okay, but how do I recognize the relationship between g of x and f of x right here? And then once we recognize that relationship, we can legally say that this known function is the parent function, where this g of x right here is going to be a descendant that came out as a transformation of this function. Okay, so here's how I'm seeing it. This function g of x has mainly the rule that clicked that really grabbed my attention here was that the square root, and then inside of the square root is whatever we give to the square root. And so here it's f of x and square root is the rule for f of x. So it now looks like, in the way how it is mathematically, it's a square root, but instead of taking the usual x, we are taking an expression instead of just a simple x. That expression is minus 2x inside the square root. So in the way how I wrote it like that, then I recognize that this g of x equals square root of minus 2x. Indeed, it can be recognized as the function f, but taking the input minus 2x. So now I recognize that f now can be regarded as the parent function where g came from. Okay, and this is in the form of f of ax, which rings for me a bell that it's going to have to be a horizontal scaling transformation. Okay, so now let's make some more. Let's make some more notes on this g of x function right here. So what I see now is that the a value in this case is being a -2, okay, which is a negative, obviously. Okay, it has absolute value. Absolute value of this a is well above 1. Okay, greater than 1. So that's all we need right now for now. So in that case, what I see here, this is a negative coefficient. So I'm expecting. So as something that's expected. Okay, in my expectation, I'm expecting number 1. Okay, we have a flip. Okay, because the a here is negative, so it's gonna be flipped. Okay, horizontally, of course. All right, and then another thing I noticed, since the absolute values, this absolute value of the coefficient 2 is well above 1, so that means I'm expecting a compress, okay, a compression horizontally, okay. So, or in shorter way of saying, it's compressed horizontally. All right, it's compressed horizontally. So 2 informations like that. All right, so now before we move on any further, let's look at the graph. Let's look at the graph of this function square root of x to recall for ourselves the shape of that graph. Okay, and also point out for ourselves a few guiding points right here, because in the end, even if we know what to expect here, we already knew what to expect here, but when we're actually putting that down on paper and pencil, it's not easy. So in the end, we still need to know the actual shape of this parent function. Okay, this is now the parent function. So we still need to know the actual shape of the parent function, as well as a few guiding points right on that parent function. All right, so let's have a look at the graph. All right, so on my empty graphing space right here, I'm going to put in, we're going to look at the square root of x. Okay, so here it is. This is the graph for square root of x, and again, because it is the parent function, so we're putting this graph in red color. And now this square root function has a few special guiding points. All right, so let's now take a look at the guiding points that can be recognized on this graph right here. So we have a few special guiding points. All right, so those are the guiding points. So now in that way, we want to see how that graph here being transformed based on this relationship between g and f of x. So in this way, I'm expecting that we're going to take that shape right there and flip it the other way around. Flip it through the y-axis, because it needs to be flipped horizontally. We're expecting that the graph for g of x is the flipped version of this f of x. Okay, so we flip horizontally, but then we're going to have to compress horizontally as well. So it's not going to be as widely spreaded as the red version anymore, but it's going to be somehow pressed in. Okay, more narrowly pressed in. Okay, but see, doing all of that is having that imagination and use that imagination to drive your work it's not easy. So now I'm going to stick with that advice I've been having up on the other board. So now on my other board, everything we need now is all we need to do here as one statement. We just simply multiply every x value by 1 over a. Now every x value of the parent function. Okay? So now in that way, I'm going to stay right with the guiding points on the parent function. And then every x value in that set of guiding points, we are going to multiply by 1 over a. Okay, so for the parent function, I recognize the following special guiding points right here. So for f of x, I saw there's a 0, 0 on the graph. Okay. I saw 1, 1 on the graph. Okay. I also noticed there was a 4, 2 on the graph, and I also noticed there was a 9, 3 on the graph. All right, so these are the guiding points right there. So now g of x defined as f of minus 2x. Okay, so now that means I am going to multiply. So in that case right here, this is going to be 1 over a is 1 over negative 2, which is a negative 1/2. All right, so let's go ahead and multiply it in. So negative 1/2 is to be multiplied with every x values here, every x value in my list of guiding points. So that means the first pair of values here, 0 stays the same for the y value, but this first 0 also stays the same because 0 times negative 1/2. Okay, now this next one right here, I'm looking at 1 for y because y value stays the same. 1 times negative 1/2 gives me negative 1/2. Okay, now this next one right here, 4 times 4 comma 2, it gives me now negative 2 comma 2. All right, this y value stayed the same. This x value came out because 4 times negative 1/2. All right, and the next one right here is going to be negative 9/2 comma 3. All right, so y value just like that stayed the same, and then x value on the descendants function came out because 9 multiplied with negative 1/2 there. All right, and so now with these guiding points successfully done right there and calculated completely, then we can now get back on the graph. And now I'm going to zoom it out a little bit and put my graph a little further out to the right hand side. All right, so now these are the guiding points. All right, and so now these are the guiding points in blue color reflecting our descendants function right there. And let me put the guiding point, let me put the, okay, and I can put that the label of those right there. All right, so they look just all consistent with what we have calculated throughout this table here. All right, so now let's draw the graph through those guiding point in blue. And so now what I have here, all right, so now let's show the graph. And so in this case here, I'm going to draw the graph as following. All right, so that's how it works right there. Okay, so that's the graph for, this is the graph, this graph in blue is the graph for g of x equals square root of minus 2x. So there was, according to the expectation right here, there was a flipped horizontal. There was a horizontal flip. It already happened in the blue graph. Okay, and there was a horizontal compression, and that's why it looks narrower. Those guiding points show the fact that for example, this point right here, it has the same height. It carries out. It has the same height with its parent's point, but it's only halfway closer. Okay, that's why it's compressed in horizontally. This guiding point, for example, is, well, compared with its parent, is only halfway away from the y-axis compared to how its parent's point was. And then this parent point was 9 square units away. This one here is only 4.5 square units away from the y-axis. That's why every point here is only halfway being away from the y-axis, and that's described. We have a compression sideways. Okay, a horizontal compression. All right, and so now, before we leave this example over here, allow me to show an FYT right here. I'm going to put in an FYT for everybody to try independently. Okay, so being an FYT, I will not have to show my steps in my reasoning any longer. But I will, once I have it written down, I will just have anyone learning from this lesson to try it on your own, and feel free to pause the video, and once you resume the video, I will just simply tell out or just give out the final answer. Okay, so as an FYT, okay, so why don't we do g of x is to be a cube root of negative half x. Okay, negative half x. Like that. All right, so now go ahead and take your time, pause the video, and stay as long as you need. Take as much time as you need to get the problem done right here. All right, so at this point, once you have resumed the video, I can point out a couple of things. So that known function, tentatively for you to recognize, that known function is the cube root function, the simple cube root, one function among the toolkit functions. And now, once we recognize that, this is how it happens right here on the graph. All right, so now on our graphing space, our empty graphing space right here. This is the graph for cube root of x. All right, so that's the graph for cube root of x. And these are some special guiding points that we can use, okay, for the cube root of x. Now let me show the label. All right, so now our actual answer here, these are the guiding points for the cube root of x. For the cube root of minus 1/2 x. Okay, so these points are quite spread out, and now here's the graph. All right, and so I hope that your version that you have tried out is consistent with the version that's being shown here.